What's going on, guys? Welcome back to a new video. Now before I start off this video, I want to say if you're looking for a job or internship, check out the first link in the description. It's a guide I put together on how to secure your first tech job or internship. Hopefully that'll help you. But with that being said, thank you so much for watching. We're going to be learning about linear search. Now, I do have another announcement to make that I'm going to go ahead and continue to make these videos just for the conceptual version of it, and then also I will start making LeetCode videos as well, since I'm gonna start grinding that. But with that being said, linear search. So imagine that you're at a DJ party. The diagram on the right shows the playlist for the event. A party guest wants to know if Uptown Funk by Bruno Mars is a song on your playlist. You would scan the entire playlist to find that it is not on the list. So another party guest wants to know if Single Ladies by Beyonce is on the playlist. Yes, it is. As the fifth song on your playlist. With this information, you could inform the party guest that the song is on the list and it will be the fifth song that will be played. In computer science, search algorithms are step-by-step procedures used to locate and retrieve information from a set of data. This method in the example is similar to a search algorithm called linear search. The linear search or sequential search algorithm sequentially checks whether a given value is an element of a specified list by scanning the element of a list one by one. It checks every item in the list in order from the beginning to the end until it finds a target value. If it finds the target value in the list, the linear search algorithm stops and returns the position in the list corresponding to the target value. If it does not find the value, the linear search algorithm will return a message stating that the target is not inside of the list. Now, how many songs would you need to check in order to find Kumbara by Celia Cruz? 1, 2, 3, 4, 5, 6. So you would need to search through all of these and you would find that one. The time complexity of this algorithm is O of n, big O of n, because you have to search through every single one of these to get to your target. But we'll learn more about time complexities in a little bit. So linear search can be used to search for a desired value in a list. It achieves this by examining each of the elements, comparing it to the search element, starting with the first element to the last element in the list until it finds a match. The steps are: it examines the first element of the list. If the first element is equal to the target value, stop. If the first element is not equal to the target value, check the next element. Now it'll keep going until it finds the value, and then it'll keep going until it returns like the position of it. Now the best case performance. Linear search is not considered the most efficient search algorithm, especially for lists of large magnitudes. However, linear search is a great choice if you expect to find the target value at the beginning of the list, or if you have a small list. The best case performance for the linear search occurs when the target value exists in the list and is in the first position of the list. In this case, the linear search algorithm will be required to make one comparison. The time complexity for the linear search in its best case is O of 1. You decide to visit a new coffee shop for an espresso. Unfamiliar with their menu, you are unsure if they serve espresso. So you use linear search to scan the menu and you're able to find that it is the first drink. So therefore, like if you're searching one by one, the first one is the target, you get the target, right? So therefore, you know that it is going to be indeed O of 1, meaning it's the first one and you get it right then and there. Now, the worst case performance. So there are two worst case performance cases for linear search. So case one is when the target value is at the end of the list, and the second one when it does not exist in the list. In both cases, the linear search algorithm is required to scan the entire list of n elements, therefore making n comparisons, because n in this case is the size of the list. So if you have like 10 things, it'll go through each one to either find it on the end or it won't find it at all, right? So for this reason, the time complexity for linear search in its worst case is O of n. Now, vinyl enthusiasts patiently search through crates of vinyl records in search of their favorite musicians. If you use linear search to find the vinyl record, the worst case would be if it is in the last record of the crates or if it is not on the crates at all. Both cases would require you to search through the entire crate. Okay. And then the average case performance. So if this search was used 1,000 times on 1,000 different lists, some of them would be the best case, some the worst case. For most cases, it would be somewhere in between. On average, it will be the middle of the list. That search would take O, O of n to the, or n divided by 2. Let's prove this. So if each element on the list on the right requires a different number of comparisons to be located in the list, using linear search, the first element is located on the one comparison. The second one is located with 2, and so on until the last element is located in n, the size of the list of n. So basically this will take one comparison, this will take 2, 3, and then n is the last one, right? So the average case is the average case number of comparisons. So to calculate this, we'll do the sum of number of comparisons for each list divided by the number of elements in the list. So we won't show the math, but we can simplify things by reducing the equation to n, which is going to be the number of comparisons, because there's that's how many numbers there are in the list, divided by 2 because of the average. So we would expect on average for the linear search algorithm to search halfway through the list. Therefore, the time complexity of the linear search, its average case is O to the n divided by 2. So basically half of n, right? One half times n. Based on Big O simplification rules, which you can learn more about in the Big O lesson, which we'll learn later on, we simplified the time complexity in this case to O of n. Now this is because it's 1/2 times n, so you take the biggest value and you get n. So at the end of the day, it has to search for each one. It doesn't matter if it searches halfway or all the way, it's still gonna search n number of times no matter what. Therefore, the big O is gonna be of n. Now the time complexity of linear search. So linear search runs in linear time, as you can understand. Now with the number of comparisons, it finds with the number of comparisons to find the target increasing linearly as the list n grows. So for the number of elements and the number of comparisons, it'll just grow linearly, because let's say you have um, two elements in the list, it'll search 2 times, or it will have to make 2 comparisons, and so forth and so forth. Let's say you had 10,000 elements, it'll have to do 10,000 comparisons. If it's like the last one in the list, or if it's not found, of course. So it increases linearly, like so. And if you've never taken a math class or don't know what this means, it basically means just it's correlated. So if one grows, the other will grow at the same rate. So it kind of, on a graph, it just grows like that. So a time complexity of O to the n means that the number of comparisons is proportional, that's a good word, to the number of elements in this list. With a list with twice as many elements, linear search will take at most twice as long to perform the search. The time complexity of the linear search is also dependent on the best case, worst case, and average case scenarios. What is an example where linear search would be a good choice to search for values? What is an example where it would be bad to search? So I would say when to use linear search is if you have like a small list, or if you know that it's at the beginning of the list, then use linear search, or don't use it at all if you know it's not, it has a chance to not be in the list, or if it's a really long list. And I'll give you, or in the next video, we'll learn about another type of search algorithm which is more efficient if you have a bigger type of list. So to review, linear search is a search algorithm that sequentially checks whether a given value is an element of a specified list by scanning the elements one by one until it finds the target value. So it's looking for, let's look, 22 right here. So it will search 1, 10, 23, 94, 83, 35 until it finds 21, and then it'll return the position of that, which is 0, 1, 2, 3, 4, 5, 6. So it'll return 6. And then we also learned that the best case is O of 1 if it's the first element in the list. The worst case is the O of n, or if it's not in the list, right? Average case is 1/2 times n, but that just equals out to O of n. Linear search is a good choice when you expect the target value to be positioned near the beginning of the list, or if a search needs to be done on an unsorted list. Oh, this is huge right here. Okay, the next searching algorithm we're going to learn about is for a sorted list, but if you have like an unsorted list, this is your go-to, because this doesn't care if the list is sorted or not, it'll still find it, just has to search through all of them. But yeah, that's gonna end it right here. That was linear search. Hope you enjoyed. Thank you so much for watching, and subscribe if you're new, and I'll see you in the next one.